2.83. This one is very difficult. This one is almost off the charts. You're walking along. There is a fog-shrouded gorge. You drop a coin. The coin falls. Let's see. Using a motion diagram, you drop a coin. It starts out in your hand and accelerates downwards due to gravity. It smacks on the rocks below, and an extremely fast, steady velocity sound wave just zooms up. So, coin falls down, sound comes up. And you hear the sound of the coin. Now in my question it says, to find the height of the cliff, you listen, you drop a coin and you listen, 10.9 seconds later you hear a sound hitting the ground. So delta T is equal to 10.9 seconds, and that's equal to the change in time required for the rock to fall, so I'm going to put a little subscript R there, plus the change in time for the sound to return. So 10.9 seconds, however much time you're given in your question, is the time for the rock to fall plus the time for the sound to rise up. That's important because we want to know the height of this cliff. I encourage everybody to draw a diagram like this. It buys you time, it allows you to collect your thoughts. So the height of this cliff is something that we want to know, and we have very little information. If we put, let's say we put the let's call this y at the bottom. Let's call this y at the top. We don't know these heights. Maybe we could call one of them 0. That might help. We do know the initial velocity of the rock is in our hands, so we know that's 0. We know the acceleration of the rock is 9.8 meters per second squared downwards. And, well, let's call the bottom 0. Let's say the bottom is 0 and the top is, well, a height, a position we don't know, and that's what we're really trying to find. Also, we found that the velocity of sound, we're told in the question, is 330 meters per second, and that's going to be upwards. So we need this distance, but we don't really have enough time information to figure this out. We're given a time, a total time, but we don't know these individual values for it. And I'm afraid we're going to have to figure that out. So we need to work in steps and slowly try to figure out these values so we can figure out the total time. And then once we know the total time, we'll be able to take it apart again and find this height. Okay, so step A. let's try to find time that the rock falls. So T rock. And what kinematic equation would we use? Well, we know position information. We'll use the standard kinematic equation. Your final position is equal to your initial position plus your initial velocity through time plus 1/2 a plus the acceleration through time squared. Now for us, our y final is the bottom, which is 0, y 0. Our x initial is our initial position here, yt, plus initial velocity is 0. It falls out of our hand, so this term is going to be 0. The acceleration we know, negative 9.8 meters per second squared. Delta t, and this is going to be delta t rock. We don't know what it is. That's an unknown. Let's see, you can solve this algebraically, move this over, divide, and you can do that on your own. But after 1 or 2 algebraic steps, you're going to have delta t rock squared is equal to, well, actually maybe even just 1 algebra step. Take this over and divide. There's a negative sign here, but then when you divide by another negative sign, it's taken care of, and you have the half, 9.8 meters per second squared. And then you can take the square root of both sides, and there you go. Not very easy, but solvable. Well, not quite, because we don't know this height. We know the time, but there's still one unknown there. We can't go any further than that. How about, so we're going to leave it until maybe we can go further. The time for the sound, how long does that take? Well, there's no acceleration when the sound moves. The sound has a constant speed, and it can cover ground at a very rapid constant speed with no concern for acceleration due to gravity. So x final, when there's constant velocity, x final is equal to x initial plus velocity through time. It's a simpler version. Translated into our case, final position on the way up is yt. Initial position for the sound is at 0. The velocity of sound is 330 meters per second. It's upward, so it's positive. Delta t. Delta t is delta t sound. Trying to find that. And now you can easily isolate for the sound. Delta t sound is equal to yt, which we don't know yet, meters per second. Okay, we have 2 mini expressions for our times, neither of which we can solve. We're going to bring these together and solve in the next video.